Okay, we left off yesterday in Chapter 3, Lecture Module 3, with flash memory storage. So we know that flash memory is chip-based storage. It's based on electrons. Recall, what we're looking at here is storage devices, and we can discriminate between the medium and the device. The three mediums, of course, are magnetic. Second is electronic. Third is optical. Of course, we're recording zeros and ones. In some cases, the device is integrated with the medium. In others, it's not. Flash memory, when we look at solid state storage, again, it's integrated. As I presented yesterday, nobody would ever think about taking a USB thumb drive and taking it apart to get to the solid state storage. As I presented this last week, there are two different types of flash memory. And again, this is not in the textbook, so it's just extra information. You're not responsible for it on the quiz. One solid state technology is based on NAND, or not and. The second is NOR, or not or. And we'll look at this when we get to Boolean logic. NAND is block accessible. So this is similar to the sectors that we see, the sector addressing, and actually cluster addressing, that we see on magnetic hard drives. Whereas NOR is byte accessible. So this is similar to what we see in memory. Recall, we understand about the byte, smallest addressable unit in memory, has contents and address. It is executable. So NOR technologies are executable. They have fast reads, whereas NAND, block accessible, has fast writes. NAND is inexpensive. We know from our thumb drives, Pareto's law, right, which mirrors Moore's law, in that storage capacities keep increasing and the size and the cost go down. Now, these two technologies are to some extent converging. We're getting better and better at a single solid state technology that will have both fast reads and fast writes. And when this does occur, that's actually when it will replace things in, or more so in computing. Embedded flash memory. Well, again, the textbook is kind of lax in its terminology. We know that memory, of course, byte accessible, right? Volatile, but of course with solid state devices, it's not volatile. It's going to be persistent or non-volatile. But in many cases, when we talk about, say, a phone, yes, it's going to have flash memory, but it's also going to have flash storage. So we do need to discriminate between the two, okay? On the, whether it's byte accessible and executable, or block accessible, more similar to or in accord with storage devices. So again, when we look at this, flash memory cards, well, actually they're storage. When we look at SD cards, they're actually storing information. They're very inexpensive, right? SD cards are expensive, which lends us to believe they're actually based on NAND technology, block accessible. So if they're block accessible, they're not byte accessible, so they're not executable. So they're actually not memory. So just keep this in mind. Again, we have this understanding now. We're growing in our foundation to where we can actually analyze and assess what is actually taking place. So we're seeing embedded memory or storage in many things, whether it's Internet of Things, our mobile devices, and more, of course, even just in our laptops. We're going to look at the advantages of solid state technologies in just a minute. So USB drives, already presented this. I won't go back into it. Smart cards, credit cards that have some SSD built into it. And it depends. These are used for a lot of different things, security. And again, they're straightforward. When we look at solid state drives, what are their advantages? Well, the first is they're more resilient. They're not as prone to disk crashes as magnetic drives. So why is this? Well, magnetic drives, of course, are moving. They have a read-write head that moves over the surface of that magnetic platter, and the magnetic platter itself is rotating. Should the device be bumped or dropped, those read-write heads can connect with, okay, and essentially corrupt that platter. And remember that platter is spinning, so it's going to corrupt quite a bit of the platter. And it doesn't have to be just that. I mentioned that you should never take a magnetic disk apart, okay, a hard drive. Why? Because there's dust particles. There are many different contaminants. Should those contaminants get between the read-write head and the platter, the spinning platter, they too can corrupt it. There's your disk crash. So SSDs can crash, but it's a little different, okay? So they're less susceptible to error failure from bumps, etc. They also take less power. Recall with a mechanical hard drive, we have mechanical parts. The read-write arm requires a motor. The spinning disk requires a motor. These take substantially more energy than a solid-state device. And when we look at this in terms of mobile computing, where's that power coming from? Batteries. Also, mechanical devices, motors generate heat. So you can see there are many advantages of moving to solid-state drives. And again, we're moving that direction, but we still need to resolve that discrepancy between the NAND-based technologies and the NOR-based technologies. One option for cost effectiveness is hybrid drives, because solid-state devices are expensive. Look at the price of a phone today. But if you ever do a cost comparison or say mock-up of a system, you can go on, Apple actually has a really good tool to where you can configure it. And I urge you to do that and see how much it costs to move from a 500 megabyte storage, solid-state storage, to 1 terabyte. It's a couple $100. You move from 1 terabyte to 200, it's $600, okay? Whereas with magnetic hard drives, you can go up in storage capacity for much less, okay? So again, solid state devices are very expensive. So again, with all computing systems, we have a balance, we have a trade-off, okay? Because solid state devices are quicker than a magnetic hard drive, take less power, a lot of these other advantages. So they came out with hybrid drives, which will have both a magnetic drive and then partnered with a solid state drive. Why would they do this? Well, then they don't need a 2 terabyte solid state drive for your entire file system, right? They can have a lot of the storage on a magnetic drive, and then for things you really need quickly, put them on the SSD. One of the companies to really first do this well was Apple with the Fusion drive. What they did is they built the functionality into the operating system where the operating system would continually monitor what the user is doing, what applications they were using, what data they were using. And if they used an application frequently or data frequently over and over, they would migrate it from the magnetic drive to the solid state drive because access would be quicker. And then for other items that the user would rarely access, it's fine. Keep them on the magnetic drive. Doesn't really impact your computing that much. Okay, moving on. Tiny PCs. And when we look at tiny PCs, this is included here largely because they have solid state storage or solid state memory. You know, examples are the Roku, the Google Stick. We're seeing more and more of these devices. And I won't say much more about that. They're kind of incredible. There's a lot of development that's possible on these, by the way. And I'll talk about that later when we get to programming jobs. Okay, the third type of medium, of course, is optical. Okay? And with optical, we do see the clear distinction between the medium and the device, right? We have a DVD player and we have DVDs. We take the DVDs, which are the medium, and insert them into the device, and of course, access whether it's a movie or data or whatever. They can be internal, they can be external. And a note on internal versus external, and I've said this before. It's very nice to have everything internal. It's very convenient, okay? Quite often we get too caught up in convenience. But I want to remind everyone, as we look at all of these things in the back of our minds, let's recall that IT business society triangle. And when I look at society, in this case, I'm looking at the environment, ecology. Our computing devices are absolutely horrible in landfills. in the chemicals they have, the time it takes for them to degrade, it's it's not good. So when we have these all-in-one devices where everything's built in, should something go wrong in a phone, in an iPad, quite often what do people do? They just throw them into the landfill. And what people don't, that's bad. We recognize that, but they're probably going to purchase another, which drives the manufacturing. And the manufacturing of these devices use many bad chemicals. So we'll look at this further when we get to green computing and the ecology component of this course. So external versus internal, there's actually a good reason to use external devices. If I have a computer with external storage, should the computer go bad, I replace this little computer. I reuse, I don't get rid of my hard drive. So great, I'm gonna have, or it may be messy. I may have cables connecting these devices, but from an environmental perspective, it's far more eco-friendly. So getting back to optical drives, again, quite often now we're seeing them externally. Some computers are still shipping with them. Apple no longer ships with internal optical drives. You have to purchase them. That's another issue. The optical discs themselves are circular plastic discs. And the way it works, of course, with optical discs is you have a laser. The computer has a laser, and the disc, of course, spins underneath the laser. And the laser detects these pits and lands, but it doesn't detect, say, a pit as a 1 and a land as 0. And when I say land, it's a surface, a flat surface. It actually detects the transition between pits and lands. We're going to see this again when we get to networking. I presented last week that if you have two computers, both at 3.2 gigahertz, right? Same Apple computer, both rated at 3.2 gigahertz. Their clocks aren't exactly 3.2 gigahertz, and they will not be the same. So we're going to introduce, there's going to be a synchronization problem. We're going to see this in networking. But this also applies to optical discs, because you can look at an optical disc and say it has a rated rotational, RPMs of, say, 5,400 rotations per minute, okay? But two identical optical discs, both rated at 5,400 RPM, are not each moving at exactly 5,400 RPM. One may be 5,401, one may be 5,402, quite likely even further apart, okay? So you don't actually know when to expect a pit or a land. You can't time it like that. So we need to embed the timing into the encoding. We can detect a transition, right? If it's a flat surface, the laser is only going to take a certain amount of time to reflect. If it's a pit, it's going to take longer. Now in production CDs, these are actually lands and pits. In the recordable DVDs that you and I have on our computers, what the recording mechanism does is actually changes the reflective properties of that surface to simulate pits and lands. Physically, an optical disc is created in a single track that spirals out from the interior of the disc. Recall, in a hard drive, I have concentric circles. They meet each other, okay? On an optical disc, it is a single track. And you see these little points here, which will indicate sector boundaries, okay? So again, similar to hard drives, that sector is that smallest addressable unit on a hard drive. Sector is 512 bytes. But we know on a hard drive, of course, they're grouped into clusters. So my addressing is based on these sectors here. Again, just keep in mind, all processing is done in memory. So if I want to do anything with this data, it needs to come into memory. Okay. So I spoke about it, internal and external hard drives. We look at portability. We consider interoperability, right? If I have a thumb drive, can I, use it in a Mac, in Linux, in Windows? Well, again, that is going to depend on the operating system. It's the operating system that will format that drive. And we'll look at that in a couple of weeks when we get to operating systems. But it is important to keep that in mind now. When we look at other types of storage systems, network storage, whether it's network attached or storage area network, keep in mind that wherever the data is being stored, it's being stored on one of those three mechanisms, whether it's magnetic, solid state, or optical. Okay, it's just that the storage device is not immediately connected to our machine. Network attached storage is a wonderful application in the home, media libraries, things like this. So network attached storage, I run one here, is connected to my router. As such, it is accessible via Wi-Fi from any device in the house. So I can store files to it. It's great for media. I can stream movies, stream music from it. So I have a single repository. And we're going to see later on that a centralized device provides distinct advantages. Further, also connected to my router will be my printer. So I can print wirelessly from anywhere, from any device, from anywhere within my house. So again, that centralized mechanism provides many benefits. Storage area network, okay, it's just expanding. It's network attached storage essentially, but now it's distributed across many different places. Cloud storage. Okay, what do we know about cloud? We presented that cloud is a client server architecture. And what distinguishes it from client server is that it has that web accessible interface. The interface is pushed to us from the server in an HTML format. And we see this box.net, Dropbox, iCloud, Microsoft's OneDrive, and there are wonderful advantages to it. You know, from a user's perspective, I can store something in iCloud, right? Music, whatever. I can go to Florida for spring break and access, of course, my iCloud. Great, wonderful. And I can do it from any device, my phone, my iPad, my computer, because it comes down in the same user interface because of the cloud aspect of it. There are some downsides to cloud storage, cloud computing. With cloud storage, we're no longer in complete control of our data. Our data's up in the cloud. And if you look at the end user license agreements of all these providers, they can go through your stuff. And what they're going through your stuff with is, and applying, is machine learning. So they're analyzing it. They are profiling us. And then extending out, they can apply predictive analytics. And you would be shocked, and I'm actually even frightened, on what they know about us and how they can predict our behavior, okay? Even to the extent that it's possible to influence people's behavior with the predictive analytics. So I won't say more on that. We'll get to that with the ethics portion of this course. Okay, so cloud storage, wonderful benefits, absolutely, but we need to be aware. And there's an adage in the industry. I'll leave you with this on cloud storage. If something is free, as box.net, iCloud, Microsoft's OneDrive are, you are the product, because they're taking this information and again, sifting through it with machine learning. And on that, I'll introduce something else, information technology. For a long time with IT, the focus has always been on the technology. That's what draws us to this discipline, right? But now organizations recognize that there's more value in the information, okay? With the information, of course, with machine learning, a lot can be learned. By the way, who has the most information? Who has the most people? China, India, okay? If you search CISS100.com in that right-hand cloud tag field, you will find, if you search storage, you'll find two Chinese companies that offered one offered a free terabyte of cloud storage, which is huge. You can back up your entire drive there, which is what they want. And another Chinese company offered you 10 terabytes of free cloud storage. Think about that. First of all, what is the cost? What is the cost to offer 10 terabytes of free storage to everyone on the planet? Oh my God, the server farm must be huge. The environmentals, the air conditioning, the power required. Well, that should convey to you how important, how financially important possessing that information is. We've seen this move in IT from the focus on technology to the focus on who has the most information. And we're going to look at that too. Okay, in computing, we are always concerned with resiliency, fault tolerance, right? Because we want proper deterministic computing, right? We want to be able to provide answers. We don't want to lose data. How do we do this? Well, and we always, of course, want to increase our efficiency. So, RAID, redundant arrays of independent disks. Okay? There are many different levels of RAID. I'll only get into, the textbook only gets into the first two. The additional levels combine these two. So in the first, RAID striping 1, we use striping. So we have 2 different hard drives, and a file will be split in half, and half the file will be written to one hard drive, and half written to the other. And in this case, we can easily see it's only going to take half the time to write it to the file system, right? Because I'm writing half to one drive, half to another. Okay. That didn't really improve our fault tolerance or our resiliency. The second is mirroring. This is a redundant approach. If I have data I absolutely need to retain, okay? And I need to retain on a per transaction basis. So not like backing up at the end of each day, because of course I could crash at some point and lose a lot of the transactions at any point in the day. I'm going to write all the data to 2 different disks at the same time. Of course, this is going to require more buses, just as this one will. But now, should one of these drives fail, I still have persistent data on one of the other drives. So we achieve in computing fault tolerance or resiliency through redundancy. We're going to see this in networking too. If I need to communicate between 2 devices and I need to make sure that I can always communicate, like a real-time system, a space station, something like this, I'm going to have a backup network, a redundant network, or alternative paths. Okay, getting into backup, okay, archival storage systems, okay, and these are magnetic tape. This is another application of magnetic, and in this case, we do see the distinction between the medium and the device, because I'll have a backup tape device, and then I'll have backup tapes. Tapes are still used, largely because they're so cost effective. If I need to back up my system every day, I don't want to have a separate hard drive, 30 separate hard drives, to back up for a full month. And then of course I'd have to overwrite them in the next month. Certain organizations need their data, again, to be persistent over a long time and hence archived. So magnetic tapes are pennies per, application. They're very easy, inexpensive to purchase. And of course you can just stockpile them and keep archives. They are sequential storage. They're not direct or random access. And here's just a picture, okay? So just recognize they're still used. Now, speaking about backups, let's recognize this is an operating system functionality. There are 3 different types of backups: full, differential, and incremental. And we choose which one really based on our business operations. I'll explain this in just a minute. So first, to distinguish between the 3 types of backups. Full backup is kind of what you and I would do, okay, most often, if we don't have Apple's time machine or something like this, to where I take a USB thumb drive, I, of course, insert it into my computer, and then I'll just drag the files I want to save across. Full backup. I'm backing up everything, maybe my entire hard drive, who knows. A differential backup. A differential backup begins with a full backup, but then every time a file is changed at the end of Monday, maybe file A changed, I back up A. Maybe on Tuesday, files A and B change. I back up both A and B, okay? Essentially blowing away the backup I had for Monday's A. So in this case, with the differential, I'm always going to have two backups. I'm going to have the first full backup, and then I'm going to have the latest differential backup. With an incremental backup, it's going to happen over and over, incrementally, okay? I'm going to get a full backup the first day. On Monday, file A changes. So the first incremental backup will have that first A change. On Tuesday, A and B changed. Now on Tuesday, though, what's backed up on A will be how A changed. So essentially, I'm going to have system states, which is wonderful because I can track changes. If you look at, say, software development, because a week ago, I had a system that was actually working better. So I want to go back to the system I had last Thursday, or maybe it was Friday. With an incremental backup, you can actually do this. What often drives determination or selection of which one we're going to choose to depends on the nature of the business. How quickly does a business need to get back up and running? Give the example from Amazon's perspective. Amazon brings in millions of dollars every minute. They cannot afford to be down. Every lost minute is millions of dollars. So if you think about restoring the opposite direction of backing up, well, with a full backup, you just restore it. Fine, you're done, okay? With a differential backup, you restore the full backup, and then the first or the last, differential backup. And so that's two steps, a little bit longer than the full. With an incremental, you need to replace the full backup, then Monday's incremental backup, then Tuesdays, then Wednesdays, then Thursdays, etc. Certain organizations cannot afford an incremental backup. So again, it depends on what the organization is doing and how they use the data. Do they need these intermediary states, so to speak? Okay, so we know this. This was introduced on the first slide. How do we select? Well, it's based on speed, compatibility, storage capacity, convenience, portability, cost that the textbook leaves out. Okay, I'm going to change my share here. And now we're going to take a look at some things that are kind of beyond the scope of the textbook, but are very important. Okay, here I am. By the way, just so you know, I'm on a MacBook and I'm running Windows within a virtual machine. So this kind of looks familiar to people, okay? I am going to open up the file manager here. All right, and bear with me as I navigate. Come on, wake up. Okay, going into a folder called Forensics. So that should let you know what's coming here. Okay, so what do we know? This is a file manager, of course. So I'm interacting with the operating system that is showing me the files. Okay, so we're talking about operating system constructs. We know that individual applications have their own format for their file structure. And you can get this, by the way. And in fact, I had to do this for what I'm about to show you here. So I can research Microsoft Word file format. If I'm a developer and I'm writing a word processor, but I want that word processor to be able to save the file in a .docx Microsoft Word format, I would go out and search and study how the Microsoft Word file format operates. So take a look at this. First is a text file, okay? And I'll open it up real quick just to show everyone, okay? So open up in my basic text editor, TextPad. and I see 9 characters, right? Text file. Okay, and I'll close it. That's all I need to see. There's nothing else there, text file. And my file manager, Windows Explorer, is showing me what's a text document taking up 1 kilobyte of storage. Of course, the date and time, things like that. But I don't trust that 1 kilobyte, okay? Because I know no hard drives today are really addressing at 1 kilobyte. We know that, of course, the sector is the smallest addressable unit, 512 bytes, but no hard drive does that. They actually combine them into clusters, okay? So I'm going to go to properties. I'm going to try to go to properties. How about that? It is resisting. Properties. There we go. Okay, so 9 bytes, we saw that. Text space file, 9 bytes, 9 characters, okay, 9 ASCII characters. Fill in all these details we know to date. Size on disk, 4,096 bytes. Well, we know the sector is 512 bytes, so I could reasonably ask, what is my cluster size? Right, 8 sectors. So this hard drive here is formatted 8 sectors to a cluster. So a minimal addressable unit on my hard drive, the cluster, will be 4,096. And this is very important when we get to forensics, because when I transfer data from the hard drive to memory, it's coming in 4,096 byte units. But also, when I save anything to my hard drive, it's being written as 4,096 bytes. So these 4,096 bytes that are being written to my storage come from memory. But we see this file has only 9 bytes. So, of course, 4,096 minus 9. So a lot of this, the operating system is just going to grab whatever is next in memory and write it to the hard drive. This is known as RAM slack. And most people, 99.99% of them out there, don't realize this is occurring. Because what's going to exist on their hard drive are little breadcrumbs from whatever they're doing on their computer. So say the person had a browser up, right? Browser's in memory. And maybe they were on a site that they should not have been on during working hours or whatever. And they saved a file. Well, of course, that file was saved to storage. But if it wasn't the full 4,096, the operating system's just grabbing whatever's next in memory and writing that to disk. On disk is going to be breadcrumbs, essentially, okay? Little pieces of information that were taken from memory that were written to disk that the user never even knew about. This is just one component of digital forensics analysis. So if you were to take a look at a hard drive, you're going to find things that the user never knew were there, maybe good or bad. So recall what I said, we need to understand this discipline from the ground up, okay? It's our responsibility as IT professionals from this point forward. Let me show you something else. Close that. Here's my MS Word forensics test file. And by the way, I have a 1B F9 there. So I have a smile on my face here. Some people probably are thinking, well, maybe this is a hexadecimal address, and it is. And I do that just so I can find something here. So I'm going to open this file. Of course, Microsoft Word will open because it has that .docx extension, which in Windows is associated with Word. So when I double clicked on that file with the .docx, it opened up Microsoft Word. Microsoft Word went from a program on storage to a process in memory, and it was fed with the resource that is that Microsoft Word file. And I see forensics test file. And I'll scroll down and you'll see there's nothing else. This document is one page, that's it. With the 3 words, forensics test file. Of course, Zoom is obscuring where I need to close this. I won't close the entire window. There we go. So the operating system is reporting this as 12 kilobytes. And just for the sake of it, I'll open properties. So the actual file size, no, it's not what I wanted. It didn't get it correctly. There we go. Properties. Okay. So the actual file size is 12,288. Okay, so I could compute how many clusters. And I won't get into file slack at this point. But I want to show you something. I'm going to open up a binary hexadecimal editor. And let me show this. I can find it in my Zoom control here. There it is. So you're now seeing what I'm looking at. Okay, a binary hexadecimal editor. First, a word of caution. You can find these for free. They're out there, okay? They're used for many things, for working on, say, hard drives at the byte level on a file system. If a file system becomes corrupt, you can use these to, if you know what you're doing, reclaim data, okay, from a crashed hard drive, things like this. I urge caution because you can crash your hard drive like that. So if you do this, which I don't recommend at this point in our studies, don't save anything back to the hard drive. Don't even open the operating system that's on your hard drive. Don't open the master boot record. I really caution you in opening anything. So I'm doing this just for demonstration purposes. So again, this is a binary hexadecimal editor. On Mac, I have Synalyze it, okay? But there's BinHex in Windows. There are many different things out there. What I'm going to do is I'm going to open that Microsoft Word forensics test file I just had open. So here is the file as it exists on disk. And you're seeing it represented in byte-wise order. So I'm seeing offsets, okay? Of course, the counting, the first byte is 0, second byte is 01, etc. In the right-hand side, you see its ASCII representation. So you see all these zeros, they're meaningless, okay? Now, I'm going to do this just for demonstration purposes. Again, I am not going to save this file, so I'm doing it just for demonstration purposes. You can see I highlighted something over here, a particular byte, and we see that it is now highlighted over here in the file. And I can type things. I can type A, okay? And look what happened, A, 61. 61 is the ASCII code, the ASCII representation for A. Of course, B will be 62. Okay, and these are lowercase a's. So what a binary hexadecimal editor allows me to do is to manipulate the file on the byte by byte level. Now, again, this is a Microsoft Word document. So there's a lot of metadata, there's a lot of formatting, there's a lot of overhead. And again, I did go out and research Microsoft Word, the file format, to realize where I could modify it without really affecting it to where it can still be represented. And I can do this with a lot of files. I can do this with a picture, .png, .jpeg, okay? So in my file name, again, I provided this address in hex. So I remembered where I put it so I don't have to scan through this entire file and find it. So I'm going to scroll down to the offset within this file of 1B F9. So if I scroll down and down and down, 1B, there's my B's right here, 1B F9. Look what I wrote and saved in this file. Secret message. Okay. Now, what does this allow me to do? Say you were a system administrator and you suspected 2 of your employees are colluding to do something nasty to your organization, and they're communicating. but you haven't been able to catch them. There's nothing in their phones, nothing really overt or conspicuous in their emails, but they're sharing these files. Now, of course, you can take a file and turn the font clear, okay? So you couldn't see it, but of course, that's really easy, right? I can highlight the whole thing and turn text to black and I can see it. Would you have caught this? Now note, this is in clear text, right? I just wrote secret message. I didn't cipher it or encrypt it at all. A very simple encryption, of course, I could represent A as B, B as C, you know, an offset of 1, because then it just looks like gobbledygook, right? At that point, scanning this, I wouldn't recognize it at all. Okay, let me take this up a level. And this is a purely fictional account. Okay, I'll say that twice, purely fictional account. I'm a terrorist, and I want to communicate with my terrorist buddies around the world. How could I do this? Well, I'm going to use the infrastructure that's out there, eBay. I am going to take a picture of a pencil. I'm going to open up my binary hexadecimal editor, and in a place where I'm not going to corrupt that .jpeg or .ping, I'm going to write a message. It's not going to be in clear text. I'm going to cipher it too. And my terrorist buddies around the world know that at 8 o'clock on Monday, every Monday, to follow me as a seller, eBay seller, and download that picture. And once they download it, of course, they open it in their binary hexadecimal editor. They decipher whatever it is at that location. I've told them where to look for this. And I have a way to communicate with them around the world under everyone's noses. And about 5 minutes later, I realized my error, of course, suspected error. And I didn't really mean to sell a pencil on eBay for $5,000, whatever. My bad, sorry. And I take my posting, my sale down. But I coordinated with all of my terrorist buddies. And eBay has such a high transaction volume. And again, you just have characters here, right? And then I'm ciphering them. So is anyone ever going to detect this? Again, this is where we need to understand. We need to learn this discipline from the ground up. Any omission, any gap in our knowledge is a vulnerability that people will take advantage of. That's all I have. Hopefully you like that. And I wish everyone a great week and weekend. Lecture Module 3, of course, is due this Sunday, Linux Lab 3, and the quiz on Chapter 3. And